So there are things that we're concerned about, and the next question is what could we do about it? And there are generally two things, two general approaches. One is live with it and adapt to it, and the other is try to do something to mitigate future changes. And we're already doing both, and we probably will be doing a lot more of both. And I think this is relevant, I think, to the projects that you'll be doing, because both adaptation and what we'll call mitigation in a minute are really kind of front burner needs. So adaptation means adjusting to changes. Here are some examples of high-tech and low-tech adaptation to changes in rising waters. In the Netherlands, which is below ground, they've been dealing with water issues in dikes for centuries. They've now been installing these kind of high-tech gates that can open and close and basically put up a physical barrier to rising river waters during peak times. Here are some folks in a South Pacific island trying to plant some trees against encroachment of water on an island that may no longer exist in the next 100 years because of rising sea levels. Okay? Here's another example of adaptation. This one's in Alaska. This was a coastal village that is now being moved. The village basically decided we can't stay here anymore. We're getting battered by increasing number of storms. Our land is eroding. So the village voted to actually move a couple of 100 miles inland. Another type of adaptation. Again, these things have also been studied a bit, and there's some literature on the ability of different regions of the world, given what we know today, to adapt to the kinds of changes that are expected. Here in Europe, I would circle some of the impacts that are associated with southern Europe, where we are now in Spain. The most pressing impacts are higher temperatures, extreme temperatures, and what they call drying, basically desertification. There's a lot of concern in this region and documentation of less and less rainfall and the ability potentially to start approaching desert areas. There have been some studies of the ability of different regions to adapt to these kinds of changes. The bottom line, as you might have guessed, is that social and economic systems and the kinds of planning that a lot of you are involved in will play key roles in determining both the future risks of climate impacts and resiliency to climate impacts. This is going on everywhere. In the U.S., probably one of the poster child that I'd call your attention to in the U.S. is Miami, Miami Beach. Miami is already starting to feel the impacts of sea level rise. Many of the downtown streets are flooded year-round. Miami is spending a lot of money now to put in pumps to try to pump water out of city streets. And in some parts of Miami Beach, they're spending a lot of money to literally raise the street a foot, digging it up, planting new concrete, and raising the sidewalks. This is going on today. Things like that are going on in Tokyo and other parts of the world as well. So stuff is happening, and it has costs. So the other type of measure is called mitigation. This is basically trying to reduce greenhouse gas emissions. Adaptation, you're always chasing a moving target if things are continuing to increase. And so here there again are a fairly well understood set of measures that are both needed and are feasible. new and improved methods to reduce CO2 emissions. CO2 is the major greenhouse gas. There are several others that I didn't mention as well, but CO2 is kind of the elephant in the room. It's about 85% of the problem. It's not the entire problem, but it's the major one because we burn so much stuff. About 85% of our energy comes from burning fossil fuels globally. It's a huge investment. So anything we can do to reduce CO2 emissions from energy use in buildings, that'll be particularly of interest, I think, to some of your projects. Energy use in industrial processes, less so. Energy use in transportation systems, to the extent you're involved in planning areas where transportation is kind of an integral part of a design, that's also kind of important. Reducing other greenhouse gas emissions from agricultural activities, industrial processes, and so on. Again, I don't know how much you all know about Valencia. One of the major crops here is rice. You know that? Were you aware of that? Javier knows it. Have you been to the Albufera? You haven't? Just a little south of here is a huge lake, freshwater lake called Albufera. It's just literally adjacent to the sea. Huge rice growing area, which they turn into wonderful stuff called paella. You've had paella, right? But rice is also a crop that, by its very nature, it grows below water and it generates methane. Rice is a major food product in the Orient, around the world. It's also a major source of methane. Methane turns out to be pound for pound or molecule for molecule about 25 times more potent than CO2 in its ability to trap gases. Doesn't last quite as long in the atmosphere, but it's a very potent greenhouse gas and another kind of concern. And finally, enhancing natural sinks for carbon by growing trees, soil management. That little cycle that I showed you earlier in that CO2 cycle is really critical. The amount of CO2 that is taken up by vegetation today is roughly 25 or 30% of the total budget. So in parts of the world that are being deforested, that's basically putting more carbon back into the atmosphere in a serious way. So these are all, again, things that that are involved in mitigation. But the question is how much? How much is needed and how can it happen? And again, the key message here comes from what the goals are. Right? So if you want to deal with climate change, what are your goals? How do you know when you've won? The goals that were set out for climate change were set back in 1992 at a major United Nations conference held in Rio de Janeiro, which resulted in a document called the Framework Convention on Climate Change. It's a convention that virtually all countries of the world have agreed to, which tells you that the only way everybody agrees to something is when it doesn't really require you to do anything, which is what this does. So this is a framework convention where everybody agreed that this would be the goal of climate change. The goal is to stabilize greenhouse gas concentrations in the atmosphere, those concentrations that are rising exponentially now. Try to stabilize that, level them off. At what level? At a level that would prevent dangerous anthropogenic interference with the climate system. Okay? Basically, a level that would prevent dangerous effects. So these words, when I first saw them, it was clear that these words were not written by engineers because they're just very fuzzy, right? There's no specific goals. Doesn't say by when. This had to be written by lawyers, not engineers. And yet, when you look at the implications of this, as fuzzy as it is, lacking details of timetable, and the technical implications are actually rather profound, because you can go back and ask, well, what does it take to stabilize that concentration, independent of what the level is? What would it take to stabilize it where it is today, or 50% more, or 100% more, in different time frames? What would it take? And that's something you can get a handle on. Again, the best analogy I know of is the bathtub analogy that I mentioned earlier. If you think of the atmosphere, if you think of it as a bathtub, we're filling the bathtub with gases that are being emitted, but there's a very small drain because these gases don't react and leave the atmosphere very quickly. So if you want to stabilize the level in a bathtub, what do you have to do? You've got to turn the faucet down to match the drain. Right? Otherwise, it's going to keep rising. So how much do you have to turn the faucet? And the answer, unfortunately, is not a little bit, but a lot. Again, it depends on how quickly you're filling it up. But based on kind of where we are now and some scenarios about where we might be in the next several decades, we've got to reduce emissions by 50 to 85 or 90%. The better estimates now are toward the higher end of this range within the next several decades. It's really the concept of a carbon budget. There's only so much carbon the atmosphere can hold before the warming will start to increase. So if we were dealing with a problem where the solution was we need to reduce emissions by 5 or 10%, and we can call it success, we'd be in a different world. But we're in actually in a world where we need big reductions in a fairly short period of time to reach these kinds of goals. That 2-degree goal that I mentioned earlier is a goal that is still operable. A goal of not more than 1.5 degrees was put up as a challenge. I'll get to that a little bit later. As well by the UN framework, and that would require these kinds of reductions in even a shorter time period, 2040-ish or so. There was a big report out last year on that. So that's the nature of the challenge. Big reductions in a short period of time, and then the question is, are there opportunities for doing this? So on a more positive note, I want to just point out many of the opportunities. I'm starting, this is a picture of the U.S. energy system. On the left are different sources of energy. So there's solar, nuclear, hydro, wind, different sources of energy. What we use energy for are these things on the right. We use energy for transportation, for industrial processes, and in commercial and residential buildings. That's the energy demand side. This is the demand side, that's the supply side. There are different routes for getting there. Different fuels are favored for different types of activities. And in the middle is that important box called electricity generation. Electricity is something we've come to rely on for a lot of energy, and that electricity is used primarily in buildings and in industrial processes. But it's these last two boxes that are especially interesting in terms of potential. This darker one is called energy services. This is the amount of energy that we actually get some value off, the energy that gives us mobility and comfort and all those other things. This is the energy we waste, that we throw away, that we don't get any value off. Around 2/3 of the energy that we start with is in that waste column. About 1/3 is useful. Right? So we're throwing away literally 2/3 of the energy that we that we mine, which is the source of emissions. Why do we do that? Are we really that dumb? Are we really that incapable? Well, if you look at where that comes from, there are some things, some technologies that we have that are fundamentally not able to use all that energy. It's thermodynamics, it's physics.